let me welcome Christina Gillmann here, who kindly agreed to give us a lecture. She is a researcher in Leipzig. She's leading her own research subgroup on uncertainty visualization, and that's what she will be talking about today. So we have heard bits and pieces about how uncertainty is important in visualization, and now we'll hear it in more detail, and I'm sure it will be very interesting. So thank you, Christina, and the professor.
It's called SCADIS AI, and this is a consortium of many researchers, and it's funded by the German government, and they wanted to have some research in the direction of artificial intelligence and big data analysis, and this is how the SCADIS AI was funded. It's called Scalable Data Science and Artificial Intelligence, and there's a lot of money going on in this consortium. And one of those funded research centers is between Dresden and Leipzig, which are both cities in the state of Saxony. So as probably not any one of you knows me, I did my master's and bachelor's at the University of Kaiserslautern, which is in the western part of Germany. And right now I'm a postdoc at the Signal Image Processing Group at the University of Leipzig. And I'm also teaching since a couple of years, so maybe that's the reason why I've got invited. Usually when I'm doing research, it's along the border of these three topics. It's either uncertainty aware visual analytics, a little bit of machine learning, and transferability into applications. And if you're looking into my records of publications, each of those papers is at least at the intersection of at least two of those bubbles. So what am I going to talk about today? I'll give you a little recap on vision analytics because I'm not sure how much you're working with that concept. And then I'm going to start with the concept of uncertainty aware visual analytics. So we're going to talk about what uncertainty actually means. How can uncertainty actually be described? How can we define that? And how can we define uncertainty aware visual analytics? Because so far there does not really exist like a unified concept of that. And I want to give you like a little teaser on a workflow that I'm working on that goes in the direction of how to create uncertainty aware visual analytics cycles in a systematic manner. And at the end, because we're at the BioMedVis summer school, I'm going to give you a lot of or some examples on applications of uncertainty aware visual analytics for life sciences, for medicine and biology, of course. And I also want to talk a little bit about open problems in that context. So let's start with the visual analytics cycle, like the traditional one. Yeah, as you maybe all know, visual analytics can be described as this cycle. It starts with a data set that's going to be transferred and somehow integrated into a data set that you can handle. Then you can either transform that into a hypothesis, which is any concept that you can use to analyze your data. It can be transferred into visualization, so any concept that you can use to visualize your data, you can go back and forth between those two concepts. So usually those are interconnected, and it's not, one doesn't really, or it's very seldom that one comes without the other one. And by doing that and working through that cycle and providing interactive mechanisms, you can create new insights that you can usually feed back into the cycle again. And what we're usually doing is we're making a cut in the cycle and saying, okay, the first part, this is the system, and the second part, this is the human, which makes completely sense because creating insights is something that goes on into the mind of the user. Yeah, so there's one important thing when we're talking about this data component, and in this data component, you can have different operations, and these are maybe you have to transform your data, maybe you have to clean your data, you have to select parts of your data. And in many cases, and this is very specific for biomedical applications, I would say, you also have to integrate your data. So they're usually coming from different sources, they're in different formats, there are different types of data, and this is usually a big problem. So data integration, as I said, is really the big thing, because if we're looking into biomedical data, we can have very, very different types of data. We can have like some sheets, there's giving you some numbers, some things that we measured. We can have medical images, we can have molecular data, we can have measurements that are going over time. And those are, from a computer scientist point of view, all different types of data that we all have to handle somehow. And in a perfect world, we would handle them all together, because if we would handle them all together, we would maybe get more insights. So that was a recap on visual analytics in general. And now I want to come to the point where we are talking about uncertainty about visual analytics and why this is so important. So I want to give you a little teaser. So what is uncertainty if we're really looking at it at a practical way? So you're seeing this picture of sloths and chocolate croissants. And in our mind, those are two really, really different things. But if you're looking at those images, they don't really look that different anymore. And even worse, I just added like a Gauss blur on it. If you're looking at this one, I would swear by everything that I have that this is supposed to be a sloth, but it's not. So it's really important to think about uncertainty. So after the fun part, here comes the technical part. So what is uncertainty technically? So uncertainty is a doubt of a measurement. And there are a lot of people that misunderstand or classify uncertainty with an error. An error knows a ground truth. And if you're measuring something and you know what you should have measured and you know what you measured, then you have a distance between those two things. And this is an error which can be completely easily quantified and computed. On the other hand, you have uncertainty, which is just a doubt. I mean, it's like you measured something, could be true, could be not. You don't really have a ground truth. And so it goes like you have those measurements and you're like, okay, are they true, are they not? And there are two very prominent ways on expressing this uncertainty. One is you just give a boundary and be like, okay, I have something measured and it's plus minus something. That's not what happens when you have some measurement instruments. They're usually coming with those boundaries and be like, okay, what I'm measuring could be true, plus minus, whatever. And then there is another way on expressing that with a probability distribution, where you just say, okay, I measured something and there's a good chance that what I measured might be true. And the further away I'm going from what I measured, the less probable it will be. Uncertainty events can have a lot of different properties. So what I'm doing in my research is really like, what are all those uncertainty events? How can we classify them? What are different types that can happen? And the first thing that we are trying to do is, how can we describe uncertainty events? So uncertainty events to have a type, a quantifiability, can be or cannot. This event can have dimensionality, a category, a continuity, and a quantification strategy. And due to time restrictions, I will just talk about the type and the quantifiability today. So for the type, there are actually four different types, or at least let's say from the leaves of this graph here. You can either have objective uncertainties and subjective uncertainties. Objective uncertainties separate into two groups, aleaphoric and epistemic. Aleaphoric uncertainties arise when you run an experiment different times. So you can take ball and drop it down on the ground and measure how long it takes until it hits the ground. And you will have, every time you're doing that, different measurements. They are small, but there are different measurements, because there are side effects that you cannot really handle in that. It maybe someone opened the door and there's a little bit of wind or whatever. And then there's epistemic uncertainty, which arises from the model, because models by definition are not complete. They approximate things, they have boundary conditions, and so on and so forth. On the other hand, we have the subjective uncertainties, which are a little bit harder, because there's, on the one hand, rule uncertainty, where the question is this rule correct? Is it correct what we're thinking might be a rule? And then there's moral uncertainty, which is another level of this rule thinking. You know the rule is correct, but you're asking yourself if it's ethically correct to apply this rule. Like, you know, we have the rule of doing this and that, but you feel like it's wrong to do it for whatever reason. So what is uncertainty when we're dealing with life sciences? We saw that we have all those different types of data. And when we're really going down and break down all types of data that maybe we know, or let's say the biggest groups of data that we know, we can have, for example, spatial data. And in that spatial data, you can have different types of uncertainty. For example, you can have the values that you have in your spatial locations might be wrong. The locations itself might be wrong or are affected by uncertainty. Then there's graph data, which also comes with different types of uncertainty. Does the node exist? Do the connections between nodes exist? Do the values that are stored in a node, are they correct? And for field data, it's also like the field itself might be shifted. There's usually a position where this field is located at. And then in all the different cells and fields, the values might be affected by uncertainty. Same goes for high dimensional data. You can have uncertainty in each of the cells. And for time-dependent data, you can have the values, either the values could be wrong, or like the time points where those values are stored might be affected by uncertainty. And for document data, each of the characters can be affected by uncertainty. So what I'm doing in my research is trying to really break this visual analytics cycle down and be like, okay, what types of uncertainty can be inherent in each of those nodes in the visual analytics cycle? So for example, in the data set, we can have incompleteness of data, happens all the time. We can have finite instrument resolution. Those are examples that can happen in the data set. For the hypothesis, there's incompleteness of the model, for example, parameter uncertainty, and so on and so forth. And for visualization, this goes a lot with how are we actually visualizing our data? Like what is the mapping strategy that we're using? What is the integration that happens when we're displaying something? And the thing is, why am I showing you this table? Because we can now see what type of uncertainty we're talking about. And what we can also do is we can quantify or we can express the level of quantifiability. I don't want to go into too much detail, but level 1 uncertainty would be, okay, I know everything about this uncertainty and that's fine, and I can handle that, and we're fine. And level 5 would be in no circumstances in this world, not even if we would all be like Newton and would invent all the coolest, newest stuff, we could never, ever take care of this uncertainty. So the cool thing is, as those are all the system parts of our visual analytics cycle, is there is hope. We can somehow deal with this uncertainty. But now comes the human part, and that's a problem because we cannot quantify that. Our knowledge about human cognition and how people are understanding data and process data is so limited that we cannot really understand how all those uncertainties that are happening there come together and can be expressed or somehow can be dealt with. So what I did is I reconstructed the cycle a little bit, because when we're looking at the original cycle, there's a lot missing. It's not technically not able to really deal with those uncertainties. And the thing is, each of those components, as we've seen that before, introduces uncertainties. So I thought, okay, maybe we need some more nodes in there. And I'm going to explain a little bit how I came up with those nodes. So first of all, there's a new data set, because that's an uncertainty-aware data set where you just use your data set, and either the data set comes with uncertainty, but it sometimes does. For example, if you look into the PDB database, those are usually coming with those p-values that are giving you the heat factor that is telling you how much a molecule, an atom can actually move around in space. So that's a cool data set. It comes with uncertainty. Some do not. For example, medical imaging does usually not come with an uncertainty measure. So we somehow have to quantify this uncertainty of the original data set. That's the first one. Point number 2 is we need something that tracks down our uncertainty throughout the cycle. Because the thing is, like, when we're running this cycle, we're creating more and more uncertainty. It gets accumulated, it gets propagated throughout the circle. If you're transferring an original data set into something else, this also affects the uncertainty that is attached to this original data set. So you have to track this somehow and figure out when does this uncertainty starts to increase. Then there's a separation between our original feedback loop, because when we're coming from the hypothesis, we're usually really sure about the result that we're getting and about the insight that we are creating. If I'm taking a data set and just compute, let's say, some average values, this is completely direct insight that we can create in this data set. So this can go directly back into our data set. And for if we're doing that under uncertainty, this also holds their mathematical rules that tell you if you're mixing up values that have an uncertainty attached, it also means the result is affected by uncertainty based on the values that you had before. So this goes directly back into our uncertainty-aware data set. But then we have the other side, like the insight that we create when we're looking at visualizations. And even if we wouldn't have uncertainty visualization, we would still have the problem that we cannot really quantify the insight that we're creating here. So this goes somehow back into the original data set, and you have to find a way to understand what happened in the human brain and what happens to create the insight. And then you also have to go to all your original components and exchange your hypothesis that you used before. Let's say you're doing something that segments your image, then you have to find a segmentation strategy that gives you uncertainty attached to your segmentation result, and so on and so forth. Okay, so now that we have this cool cycle, I think it's cool. The question is, how do we go from there to there? And what I'm doing recently is I try to find a workflow where we can go from a visual analytics cycle to an uncertainty-aware visual analytics cycle, because there are strategies that give you directions on how to create visual analytics cycles for all types of problems. So I thought it might be a good idea to start there and then just extend it with some steps that I created. And the first step is just quantify all types of uncertainties in all the components. And that's what I made those tables for. Because if you're looking at those tables, you can say, okay, that's an uncertainty that I need to be aware of. This is an uncertainty that I need to be aware of. Okay, this one is not really needed in my case. And then you can just go through all the uncertainties and just quantify those uncertainties if it's possible. As I said, in the inside, there's a little problem still. Then the next step is exchange your original components by uncertainty strategies. And what we're doing also right now is we're writing a start that where we're summarizing all those things that you need to exchange and give you options on what can you exchange with what. Because as I said, for segmentation, for example, there are uncertainty-aware segmentation approaches. The question is just, what do you want to use for that? Because there's not only one. And for the next step, it says, separate your feedback loop, make sure that you're aware of what comes directly as an insight with an uncertainty attached and whatnot. And the last part is the provenance that I've been talking about. So find strategies that track down all the uncertainties when you're running the cycle, when you're creating new visualizations, when you're adapting the visualization, when the user is interacting with it, and so on and so forth. So, okay, that was the theoretical part. I want to show you some really cool applications that we recently made. And the first one, which is right now my favorite project that I'm having, is the stroke lesion analysis. And I first want to talk about the problem itself. So when you are having a stroke, what happens is that one of your vessels in your brain gets blocked by a plug, and for a certain amount of time, it depends, sometimes it's just some seconds, sometimes it takes longer, parts of your brain cannot be supplied properly anymore. And what can happen through that process is that parts of your brain are dying, and this is where like people get disabilities or can also die from. In general, strokes are the second leading cause of disability worldwide, so this is like really a problem that you should think about and take care about, and it will become worse and worse as people become more older, and let's say in modern civilizations, people are smoking too much, drinking too much, and so on. And What happens when you have a stroke, or if a doctor thinks you have a stroke, you're coming into the clinics and they're going to do different CT scans. For example, usually they start with a normal CT scan. They start, then they do a CT angio, which means they give you a contrast bolus that highlights the vascular system in your brain, because then you can see, okay, is there a vessel that is occluded? And for the last one, it's the CT perfusion, which is also with a contrast bolus, but it works a little bit different because this goes into your tissue and shows how much perfusion happens in this tissue. And from those images, you can see there's a stroke or not. But what you cannot see in that specific moment when you're coming to the clinics is what part of the brain will actually die, because this is something that develops over time. It takes like almost half a year until the patient reaches the point where a lesion doesn't really go back or becomes worse, whatever. And what we are having is we're having a super awesome database from the University Hospital in Leipzig, where we have over 300 patients where we know this incoming images. And we also know a follow-up from half a year after that, where we really know how does the lesion look like. The fun part about that is we have this ground truth that is labeled by the collaborators that we have in 3 different versions. So every patient is labeled by 3 different clinicians, and they do not agree all the time. So we're having a fuzzy ground truth here, which is challenging. And what was the initial idea of us was we're using a CNN or a specific CNN, a so-called UNET, and give an infarct risk map that predicts what might be the lesion in half a year. So as I said, we're using this unit. I'm not sure how much you're aware of the concept of a unit, a specific neural network that can do segmentation tasks. Let me put it like that. And the thing is, there's also the question, there is a very, very expensive, not only in terms of money, it's also in terms of resources that you're needing from the hospital and risks that is coming or risks that are going into the direction of the patient. Like it's an 8-hour operation and it takes a while. And the thing is, when is it necessary or when does it make sense to use it? Because there are some measurements that they have that say, okay, we should do that procedure now. And for some reason it works and sometimes it doesn't. So they said, okay, those measurements are actually more or less guessing. Can we do that better? And what we did is we used this neural network and made 2 different options. One of the networks is trying to simulate what happens if you're doing this procedure, and one of those networks is trying to simulate what happens if you're not doing this procedure. And what can happen is, for example, here, you see how we can predict the lesion. And the interesting thing is, this is the difference. This is what the network said would happen if you are doing the procedure. This is what the network said would happen if you're not doing the procedure. So you can compute the difference. And if the difference is large enough, this is an indicator that you should do this procedure. And what we're doing soonish is that we're going to have a clinical trial if we're really on the right way there. Because we can try this out. We can just take the images and see and let them do their surgery as they are planning it, as they have their scale. And we can run our network and be like, just monitor it and see, can we do that better? Can better predict to do this procedure or not? What we also do is for the evaluation of neural networks, you're usually having this like true positive, false positive, true negative values where you can compute different measurements and be like, okay, my network is accurate in this and that sense and under this and that measurement. And the thing is, those hard thresholds are actually not cool. Because you're using this threshold, we're arguing with our clinical experts about what is actually the best threshold, and they're like, I don't know. So we are using some random threshold where we are not sure if this threshold actually makes sense to evaluate our network. And what we did is we adapted our measurements so that we're actually like using a Gaussian distribution function over the threshold and be like, okay, when you're close to the threshold, no matter on what side you are, then you're still considered somehow in our computation of this is a true positive or a true false positive and so on. And then you can really have this visualization that tells you, okay, when I'm manipulating my Gaussian distribution function and be like, it's going to be more broad, then you're going to have this fuzzy transitions between like the true positives and the false positives. And this is what you can do with all of the 4 classifications that you have. And using those pre-computed classifications, you can have also a damping factor. For example, if you can have you can have units that also give you an uncertainty quantification of the result. And let's say we are using this result and we have values that have higher uncertainty than others. Then we do not want to make them so important in our computation of is this network accurate or not, because it doesn't make sense. This value is completely uncertain. Why should it have an influence in the same manner as a value that has no uncertainty, for example? And then you can manipulate those functions and be like, okay, I can have these damping factors, and the higher the damping factor, the more you're not considering uncertain values. And then you see how those evaluation functions of the neural networks are changing. What we also did is, as I said before, we have this multi-model input with different types of CT scans. And the thing is, usually doctors just look at one of them. In fact, they actually just look at one slice of one of them. And what we try to do is make a visualization that combines all different aspects of this free imaging that I showed you before. For example, we have some anatomical context, we have the vascular system, we have the perfuted tissue of the brain, and we also have like the lesion. And you can set these cutting planes, you can have different interaction opportunities, and then you can understand how those different types of data are correlated to each other. What we also did are some first experiments on how can we understand the provenance of our segmentation procedure, for example. Here we're working with not with a neural network, but with a fuzzy segmentation algorithm. And what we can do is we can also extract an isosurface that has the surrounding surface that indicates how this might be displaced, this isosurface. And those are like two steps. So in the first step we have, or in the original data, we have an uncertainty histogram. We made an uncertainty quantification for that. And what happens after the segmentation, the histogram changed. So also the average of the uncertainty changed. And what happened after the isosurface extraction, also the histogram changes. So you can follow a little bit on what's going on in your uncertainty histogram. The next one, sorry for the disgusting images. The next one is our skin bond examination project. And the problem is, in the state of Saxony, we have a lot of very landscapish areas where we do not have a lot of doctors. So people have a long way to go to the doctor, and these wounds that you're seeing here are often happening for older persons that cannot walk properly anymore. They're sitting too much, and then they're getting those wounds. And the thing is, are they super dangerous, or are there something that can be treated by something that we call mobile examination stations? So there are nurses that have cars and they're driving around, but they are not allowed to do everything. What they are pretty much allowed to do is take some stuff and put it on the wound, or change the coverage or whatever. So that's pretty much what they're allowed to do. And then the question arises, okay, is that enough, or does this person need to go to see a doctor so that he can do more treatment? And what we're aiming to do is we want to do like an app where the nurse can just take a picture of the wound, and then the app says, okay, this is this and that specific disease. And we have in this context 10 different diseases, and 4 of them are classified as you have to go to the doctor very, very urgently. 2 are classified as, okay, you have to go to a dermatologist in the next 1 to 3 weeks. And then there's one that's called bland wound, where pretty much the nurse can do everything that can be done. And here also the point is, we have a database with like, I think 400 patients right now, where we have this classification that says, okay, this wound is supposed to be this and that in the disease. But the thing is, they give us a list like, okay, it's 90% disease this, but it can also be for 10% this. So here again, if we're training neural networks and thinking about how to present the results, we're dealing with uncertainty. Another example is this one is a little bit older, where we have thought about how to improve the process of planning a keyhole surgery. So for some keyhole surgeries, you have these surgery tunnels. You want to go to a specific point in the human body. And then you, for example, if you're considering a brain tumor, you need to go to the brain tumor, but what you also have to do is you have to touch tissue in the human brain that is actually not diseased. And now you want to find a tunnel that does that tries to not touch as much healthy tissue as possible. And what you can do here is you have this, you have our program, you can set different tunnels. You have a hierarchical segmentation that goes on the first one for, okay, this is the patient in general, this is the outer tissue, this is the tissue between the brain and the skull. And then we have different parts of the brain in the last hierarchy. And what you can do is you can set an importance to each of those nodes, to each of the segmentation nodes. And you're like, okay, I want to for sure be for sure that I'm not touching a specific part of the brain. And for others, well, it needs to be, but that's better than another tissue. And what you see here is you have those tunnels. Our program computes what are the best options that you tried out here, and you see how you go into how you enter the brain. So here, this is all human. There's a skull. Here's the tissue between brain and skull, and then you are entering the brain. And in this example, you can see, okay, here this is normal brain tissue, and here we're entering the tumor. And this seems to be a good option. And what you also see is as the segmentation is uncertainty aware, so we have this transition between classes, you can also see how uncertain those classifications are. So if you have mixed colors or something, you're not really sure if you're touching the type of tissue that you're thinking about. The last example is a molecular visualization. And as I told you before, in this PDB databases, you have these p-values that give you like displacement of the atoms in the molecule. And what we are usually doing is we're having these little bubbles, and they show you how the molecule looks like. But that's not the truth. The truth is those molecules are moving. And what we added is this surface that indicates, for example, how can the surface actually change? And this is super important because the surface of a molecule actually is responsible for the functionality of the molecule. So those are there are the binding sites and all those things that need to have specific shapes so that our molecules can interact. What you can also have is with our program is that you have this Riemann-Gentman plot. I'm not sure who of you knows how that works, but in the backbone of the molecule, you have this dihedral angles. So you have the backbone, and between different amino acids, you can have different angles, and those are really important because those angles need to have a specific configuration to make this molecule stable. And then there are those plots, like the colors. I didn't invent the colors, but those plots indicate everything that comes with a color is a stable area. And if we are considering that those molecules can move, those angles can also change. And then it can happen that you're moving from maybe a stable state into an unstable state. And this is something that you should be aware of when you're designing novel drugs. Yeah, that's the last example. That's another example from medicine, where we examined a peripheral artery disease. It's pretty much the same that happens when you're having a stroke, but it happens in your arms and legs. And the problem here is that in the arms and legs, this happens over time. The problem is that you do not really have like a blockage. That's really seldom. But what happens is that you can have a narrowed down vessel from, let's say, your back to your toes. And the problem here is that you do not then, the vessels do not really supply the tissue of your foot anymore. And then people cannot walk properly anymore. So they have pain when they're walking. Sometimes it's so bad that they can only move like 10 meters and then they have to have a break. So that's really bad. And the thing is, you cannot see this properly in early stages because this narrowing down of the vessel is so small that it cannot be really captured by the images. You feel it, but you can't see it because it's on a very, very long distance, just a small narrowing down. And what we did is we can compare, in this case, the healthy foot with a not healthy foot. Like there's a patient who came and said that he has pain while walking. And we can compare what's going on in the histograms of the different tissues. So we have segmentation that covers bones, that covers muscle tissue, normal tissue, and vascular system. And then you can highlight when you're applying a threshold, where does actually the difference happen in between those two legs. And for the, here you see the muscle tissue, here everything is super distributed. So we looked through that and it was pretty much along the entire leg, which makes sense because the leg is not really supplied properly anymore. But for the muscle tissue, that was, for the normal tissue, that was super interesting because we had a cluster in the near the knee. And the doctor that we've been working with on that project said, this is super interesting because I always had a feeling that this somehow has to do with something with the knee. So we gave him like a new clue on where to go and where to look for the problem. Okay, what are general open problems when we're talking about uncertainty-aware visual analytics? So we saw a lot of examples. I taught you a little bit about the concept. And there are two types of open problems when we're thinking about uncertainty-aware visual analytics. And one type is resulting from the visual analytics cycle itself. So this has nothing to do with uncertainty. I mean, it doesn't go away when we're considering uncertainty, but it's not coming from the point that we're taking care of uncertainty. So we need a proper description of insight, as I said. We don't know what's going on in the human brain. We need an approximation of the amount of knowledge that is generated by a visualization, which goes in the same direction. So that's also something that we really have to research. And then there's the other class of problems that's more into like resulting from the consideration of uncertainty. And here the problem is, when do we actually need this uncertainty-aware visual analytics cycle? There are problems where we do not need that. We have to be fair at that point. But what are they? We need a survey, as I said, we're working on that, of existing techniques so that people know that's what I can exchange and that's how I should exchange it. There is no nice framework for uncertainty visualization. We all know about BTK and ParaView, and I would love to have a framework that works in a similar way just for uncertainty visualization, because you can, of course, take care of uncertainty with BTK and ParaView, but you somehow have to build up your own new visualization, and that's not what I mean. We have to teach more about those principles. Every time I'm talking to to some new person from the clinics who is interested in working with me, I'm like, well, how about uncertainty? We don't take care about uncertainty. And then they're starting talking and be like, oh yeah, and I have this data, and then here, well, we have these ground truths and they do not match together. And I'm like, you are talking about uncertainty. But the thing is, they just don't know the word, or they just don't know what that word means. And we have to teach that. Yeah, we have, of course, take care of the approximation of knowledge uncertainty. And what I'm also interested in researching the link to ensemble visualization, because I have the feeling that you can transform uncertainty problems into ensemble problems and back, of course, with loss. But then you have two worlds where you can grab from all the techniques that are out there. All right, thank you for your attention. I'm open for questions, and feel free to contact me if you wish.
Christina? Hey, are there any questions, Christina, regarding uncertainty?
Thank you for your talk, Christina. Maybe I missed it, but I didn't hear you talking about defalsification. I mean, at the end of the day, very often we have to make decisions based on visual analytics, and then there's the time, at least then there's the time for defalsification.
I mean, that's something that I try to here. because I'm really not a big fan of defalsification. The thing is, I mean, I give you an example. Let's put it like that. When we had this Corona thing going on, our government started putting rules like if the value of if the 7-day incidence goes over this and that specific amount, then you are not allowed to go out anymore. And this was super random. It was like 165 or something. And it's always like you put a rule somewhere and just one more and or less, what's the big thing about that? So I'm really not a big fan of that concept. So I'm trying to get rid of it, actually.
But I mean, to be honest, in many cases, you can't get rid of it because you have to make a decision to operate or not, where to cut, to give a medication or another one. So very often at the end of the day, you have to make a decision, which is often discrete or binary. And then you can't avoid defalsification and you have to do it somehow. Maybe not by a rule that was based on a random number, but you have to do it somehow. Otherwise, you will never proceed to decision making.
Yeah, but that's often up to the application. So then your doctors are like, okay, I want to have 70%. That's not, I would say from the visualization point of view, that's up to the user when where he wants to do his cut and how he wants to do his cut.
Thank you. Any more questions for Christina? Maybe I will ask something that I asked also Alessio on his previous talk is how do you think this uncertainty can be used for visualization for public? Is it useful or is it something that is more damaging and decreases maybe the trust in data?
We've been discussing that for another example. For example, if you consider climate changes, for example, and then you run all those simulations on how high will be the temperature decreasing in the next 5 years. And what they actually show is some, let's say, average value of that. I was really asking this question myself, should we do like a boundary, like it could be from this to that? I'm not sure if that would make people feel like, maybe it's not too bad. Maybe we're like on the upper end of, on the lower end of that boundary. It's not that bad. Or if they would be like, oh, okay, maybe it can be even worse. That's a question. I think that's a question of the user then, because I think there are people that are educated enough to understand that. And then there are people, to be fair, that cannot really read those graphs. So I'm a little bit in between in here. I mean, I think it would be fair to at least say that, but I'm not sure if it really would help in case you're having people that do not really understand those boundaries.
One more.
Well, I mean, you say. I was wondering, I mean, before you went into your examples, you had this one table where you had lots of different configurations of uncertainty. Maybe you can show it.
Sure. Which one?
This one. This one, yeah.
Yeah.
And all of them are of type numerical.
Yeah.
Earlier in your presentation, you also mentioned other types of uncertainty, for example, textual uncertainty.
It turned out, I mean, I was going through the list. There's a paper that says they could be from another type. I mean, I've been considering visual analytics here, and they all turned out to be numerical.
So is this an open problem to consider other types of uncertainty, like textual uncertainties?
No, it's not. I mean, you can add them, of course. It's just about.
But I guess you need a couple of other models then, right?
I think I
confidence intervals will not work anymore, or your probability distribution function will not work anymore.
I think I know what you're meaning. I think we have to discuss later what I mean by type.
Okay, now let's thank Christina.